So we've seen what a Laurent series is, and I thought we'd play around a little bit now with an example. What's life without a little fun? So the example is the one we've been looking at, e to the z over z squared. You guys actually came up with this Laurent series, and I just wanted to play with a notation first off. So the a's, a naught is the constant, and then the a's capture the positive power. So let's just be very clear here. A naught is 1/2. A1 is the constant on z to the 1, so A1 is 1 over 3 factorial. A2 is 1 over 4 factorial. AN is what? 1 over n plus 2 factorial. And then the b's, what's going on over here? The b's, B1 starts with, there is no B naught. B1 starts with the coefficient on z to the minus 1. That's this guy. So B1 is 1, B2 is 2, and then, well, B3 is 0, and in fact, Bn is 0 for n greater than or equal to 3. So that's the notation. I'll actually show you a different notation in a little bit, but for now, we'll use that one. I did want to point out to you that there's actually more to the story. So the Laurentz formula shows us how to compute the a sub n's. Oh, I noticed I left off the dz before, but I fixed that now. So a sub n I can write down using this formula, and b sub n I can as well. And somehow this seems really familiar. It looks a lot like the Cauchy integral formula, which we're actually going to need to be able to compute these things. So just a word, I'll mention this again later, but typically speaking, you really don't want to use this formula to find the coefficients. You want to start with a known series, manipulate it to get out what you want. That sounds kind of bad, but that's what we're going to do. They're just series, they don't mind. So let's play with this a little bit, though, and see how it goes. So let's recall the generalized Cauchy integral formula. And here it is. So if we want to compute this integral, and I need to know f of z is analytic on and inside my c, then here's a formula for this integral. And so let's work it out. So let's look at my general formula for b sub n. Here it is. Need a dz at the end. And I want to actually write down the details for b1. So b1 is going to be 1 over 2 pi I integral over c. F of z, for me, that's e to the z squared over z minus z naught is 0. So z minus 0 to the minus 1 plus 1 dz. And by the way, as I've written it this very moment, you can see why Cauchy's integral theorem doesn't quite apply to this, because this f is not analytic inside c, where c is living on this annulus. So you've got this annulus, and c is doing inside. And so this f is going to need to change a little bit somehow for me to be able to work this out. What I'm viewing as f from my function will not necessarily be the f that I use in the Cauchy integral formula. You'll see what I mean. So let's clean this up and keep going. So I've set up the formula for b1. I can now write this as 1 over 2 pi I integral over c of, well, this is just e to the z over z squared dz. And now for me to apply the generalized Cauchy integral formula, that's going to be the function that I'm viewing. So I'm going to think about this guy as my f or g, whatever you want to call it. I guess I'll think of it as g. And so the Cauchy integral formula tells me that, right, I can view z squared as z to the 1 plus 1. So this is going to be 1 over 2 pi I tags along. And then the integral by Cauchy's integral formula is 2 pi I g prime of 0 over 0 factorial. Well, this is just 1, like we knew already. So you already knew b1 was 1, but I wanted to show you how you can actually work it out. You can work out b2. It's very, very similar. I'm not going to do it. I would encourage you, though, pause the video, play around with it. It is slightly different. So pause the video and see if you can compute b2. Maybe we should look at b sub n when n is greater than or equal to 3 and see why it's 0. So let's think about it. When I am writing this down, I'm going to have this integral becomes 1 over 2 pi I integral over c e to the z over z squared, okay? And then I'm going to get times z to the, times z to the minus n plus 1. And now you can see, dz, you can see here, 1 plus 2 is z cubed. My n is greater than or equal to 3. And so I'm going to get either e to the z or e to the z times positive powers of z. As long as n is greater than or equal to 3, I'm going to have a negative power of z, or a non-positive, a non-positive power of z downstairs. And so that's actually going to allow me to move it up or just cancel it out. And the point is, you're left with an analytic function on the entire complex plane. And so by Cauchy's integral formula, this integral is just 0. So in particular, B4, let's play out B4. So B4, 1 over 2 pi I, e to the z over z squared. This guy, when you simplify, you get a z squared e to the z. This integral is 0. So we're done. That's what happens there. Same thing, same process works for the a sub n. I don't want to beat a dead horse here, but I thought we'd just play with a sub 2. I get 1 over 2 pi I times the integral over some closed contour c, e to the z over z squared over z minus 0 cubed, so I'll just say z cubed. So this is 1 over 2 pi I integral over z e to the z over z to the fifth. Now you're going to apply Cauchy's integral formula, but this is going to be the function that you're using. You combine the other powers, and you'll end up with 1 over 2 pi I. The integral becomes 2 pi I over 4 factorial, and you get 1 over 4 factorial, which you knew already. So I fully hope that you're seeing, I know what A2 is, but I want to play with the formula that we wrote down in the theorem for Laurentz series. So 2 remarks, and then I'll end this video. We'll often manipulate known series to obtain Laurentz series rather than computing integrals. That's really important. I was nervous to maybe do this example because I don't want you to think that's how you should typically find your series. That would be horrendous. You'll hate analysis. Also, every Taylor series is a Laurentz series. Why? Well, because Taylor series are just Laurentz series with all the bn's equal to 0. So let's stop this video here, and then we're going to play around with some examples